overview, pretty standard motivation, the network architecture. There's two kind of main features in our network. So that's the idea of fully convolutional networks and skip layers. So their motivation, they want to use convolutional neural networks to make pixel-wise predictions. So every single pixel gets classified as what that pixel is. So this provides the what and where information, and it does not need any of these other techniques. I'm not familiar with all of them, but I'm sure some people are, so it's up there. Here's the network. So on the top is just kind of a traditional classifier. We'll get into specific ones later that are used, but for now, it's just a generic classification network. So we have convolution layers, there's some pooling layers in there, and there's some fully connected layers at the end. And it takes in an input of a fixed size and outputs the label. So they do three things to kind of the general convolutional neural network to make it what they call fully convolutional. So the first thing they do is just reinterpret the fully connected layers as one-by-one convolutional layers. And in doing that, they can now accept an input of any size because it removes the kind of fixed size requirement for connected layers. That's number one. The next thing they did was add an upsampling layer at the very end to upsample back to the original size of the input. And then the last is a softmax loss on every single pixel so that they can train the whole network end to end. So that's the general idea. They went ahead and did that on three of the more well-known networks. So AlexNet, BGG16, and GoogleNet. So they said it did well on all of them. They were happy with the results. It did the best with BGG16. So going forward throughout the paper, they used their fully convolutional version of BGG16. And then they implemented the next idea, which is skip layers. So they mentioned in a paper that the shallow layers here contain good local features, information, while the deeper layers contain more of the global and the what. So they wanted to combine both of these features together. So what they did with the skip layers, they just pull layers out throughout their network, and then they call this the DeepManta wording. And then at the very end, they do a little manipulation, so they're all the same size. They concatenate them, and then score that final layer. All of them kind of merge together. So that's the two general ideas for the network, and then they apply it to, like I said, BGG16 foregone results. Any questions about how that works? That's what they call kind of their collection of all the different kinds of features throughout their network. The DeepManta is just their own kind of wording. And they coined it because they thought that as you go throughout the network, you get kind of different kinds of features, like the more local and global. So before we get into the actual numbers of the results, some of the terminology they use. So SCN32S is their fully convolutional version of BGG16. And the 32 means that they have not implemented a skip layer yet. The FCN16 is with one skip layer, and then 8 is with 2 skip layers. So you can kind of see how the implementation of skip layers helps the prediction. So with no skip layers, kind of 2 large blobs. With the 1 skip layer, you already see some refinement. You can see the guy's hands and the handlebars. And then the 8, there's a little difference, and like I said, we'll put some numbers to the next slide. You're able to get the guy's hand on the handlebars, some more refinement. So the actual results. So they tested. First, they tested their no skip layer, 1 skip layer, and 2 skip layers, which is the 32, 16, 8 respectively. So you can see as they added the skip layers to improve the performance, there's a pretty marginal improvement between the 1 skip layer and the 2, which is the 16 and the 8. So at that point, they just kind of called it that they hit diminishing returns and decided not to add any more skip layers. So it's the first thing they test. to get to the 2 skip layers. Another thing they were testing was if it makes any difference if they train the network without skip layers, use those parameters, reinitialize it, add 1 skip layer and do it again. So train your network in stages every time upgrading with another layer. And they found that actually training the whole thing at once was very similar results as to upgrading it. So they just decided to do that going forward as well. So before in the other slide, I mentioned that they don't do patch sampling. So patch sampling is basically so other methods do this. And what that is just take kind of random patches throughout your data set rather than a full image. So since this was a popular kind of technique, they tried it out on their network. And what they found is that there isn't really a big difference in terms of loss versus using full images or patches. And they were actually able to train their network quicker if they use full images rather than patches. So that's one of the benefits of these. You don't have to do patch sampling. So now some results tested on some of the popular data sets. So you can see kind of improvements all across the board. They were focusing a lot on the Pascal one. So they made pretty significant improvements over FDS at the time the next best network for this task. Any question on the results? Or pretty good.
Can you go back to the previous slides?
Sure.
So the second, so is it converging faster? Or how
Yes. Yeah. So when they use full images, they're able to actually converge quicker. They said there was a marginal decrease. So basically that distance there. But over time it goes away, so they just said it's better to use full images because they converge quicker.
Instead of doing 25% sampling, go for full images.
Yeah. All good here? So, yep. Yes. That? So they actually have 100 milliseconds time there.
No, but that's training.
Training. Good question. I think I have it in the slides. We go back. So to put images to those results, there's a few interesting cases here. You can see it did pretty well. So SDS was like I said, the next best network. So they're able to distinguish between the human and the motorbike. Pretty impressive since they're so close together. You can see the kind of fence there didn't work your network like it did here, when it just kind of cut off the bottom of that sheet. The other interesting thing actually is in this one, it classified people inside the boat, but there actually isn't any people in the boat, it's just life jackets. It's interesting that actually made a false prediction there versus the other network. So, quick on time. Summary. So their contribution was to implement these fully convolutional networks. So the idea of fully convolutional networks was not implemented by them, but it was the first time they did it for pixel-wise prediction. And some other significant advantage of this network is that they're able to accept inputs of any size because it is a fully convolutional network. They showed that adding the skip layers did significantly improve performance by combining the local and global features. And since they were focusing so much on Pascal, they got a 30% improvement on that. And improvements kind of all across the board. So that's it for that one. Any questions? Yeah.
So what did they use, like all the methods they used to compare, like what was so significant about this? Like just
Yeah, so the fact that it's fully convolutional, so they can do any input type, and the skip layers so that they can combine features from like local and global as well. So that was the significance.
I was actually going to just ask about the stakeholders. Can you go back and just
Sure.
So, let's go over the so in here, what exactly does it mean?
So they take kind of layers earlier on in the network out, and then they upsample it differently, and then they pattern them all at the end.
So is that where like do they train it differently because of the skip layers? So like you know how they have multiple steps in the training process, right? Is that due to the skip layers?
So they said they did end-to-end training there. What
So in one of the later slides, talks about the refinement processes. So you add a skip layer, you train the edge.
Yeah, so they didn't do that. So sorry, they tested here. So they tested between doing that, where they added a skip, or they did it just to get some initial values, and then reinitialize their network with those, and then did it again with one skip layer and then another. So that's the stage results. And they found it wasn't really a big difference between just training the whole network at once with the skip layers. So that's what the all at once results are.
So did they say anything about if it took longer for the conversion with all the skip layers in place in training?
That's a good question. I don't remember reading anything about that.
The segment is almost kind of like you train it on the full architecture. So I was kind of curious if if you don't have those max pooling indices there all at once, with separate steps, if that actually makes things faster or not.
Right. I could probably look through this and find it. Can't remember what I'm talking about. Write it down. Yeah, I can get back to that. Any other questions?
I actually have a question. So, can you go back to the slide where you showed us the network? Actually, no, the conv layer, actually the conv layer with the skip connections. So here, so it wasn't very clear on how. So from the so when we get to the conv layers with the polling, how does it actually go back to the upsampled predictions?
So it says here that once it pulls out, it uses COM7 4 times, and then pulls forward twice, and then I guess that gets back to the same size.
Because what we understand from convolution on the other side, it uses the image size every time we go through each layer.
Yeah.
Right. So how do we get back to the upsample?
So this COM7 I'm pretty sure is an upsample.
So maybe like a decomp layer.
Yeah.
Or?
The transpose.
Yeah, because
Yeah. Remember reading bilinear deconvolutional there. You brought up a couple ways to do it.
Was the decon stuff on the previous slide that we were just looking at?
no, it just says upsampling. So I wasn't really clear on how did they.
Oh yeah.
We use fractional input drive 1 over f. Convolutional network.
Okay.
It's odd.
That's all they mentioned is a deconvolutional network.
Okay. So they weren't really that clear on their upsampling.
Our experiments find that in network upsampling is fast and effective.
Because I believe in Segment they do something quite different.
Well, segment just takes keeps track of the inputs from max pool. So
Yeah.
whenever there's a max pool, it just summarizes the relation and it fills and zero fills everything into it.
So yeah, I was just wondering here, like, do they actually train the network to do the upsampling, or I was just wondering what kind of strategies they were using to do it.
I think because they use FCNs as the basis. FCNs use bilinear upsampling and then followed by a convolution. So my guess is that's what they would do here, just because that's their basis.
Yeah, simple bilinear interpolation. Joe put.
Okay.
Yeah. So they would do bilinear upsampling and then convolution afterwards to get the convolutions.
That's
Thanks. All right, thank you.
yeah. Can you just share the PowerPoint screen or the slides to Zoom? Simon can help you with that.
Yeah, that's good.
That's a good deal.
That's years. A little white.
Steve, can you see the?
Sorry. Yes, that looks good.
Oh, you got the same picture.
Alright, so for mine, I got assigned DeepManta, force finds any task network joined to the 3D analysis from a molecular image. Basically, a whole sentence there. So the way that I'm going to go through this is general purpose, network architecture, data types. This network is essentially just built off of faster RCNN. So I have to cover a lot of faster RCNN in general. So I'm going to cover RDN, augmented training data. It's essentially faster RCNN with using CAD data in order to project points and get 2D, go from 2D to 3D data from it. It's a whole thing. Training and losses, 2D to 3D part matching performance contributions, and then general conclusions there. I might have to stand here.
There is something on the side. On the side, there's
Try the regular keyboard stuff. I'm just gonna go run and grab.
Alright, so I guess I'm just going to stand here for now. General purpose, it's used to get 2D bounding boxes and 3D orientation, bounding boxes and points of the actual car in 3D space. It only deals with finding cars, no pedestrians, segmentation, anything like that. It's only concerned with finding vehicles. So this is the general network architecture. Similar to faster RCNN, we have some conv layers here. Those go into feature maps. Then we have these blue convolutional layers. Anything that's the same color shares weights. The purpose of these blue layers, I'm not sure about. In faster RCNN, they use a section of whatever network they're using, BGV16, whatever, split it in two, and then they use the other section for what I'm assuming are these orange layers. It doesn't make sense to me that they would have these other convolutional layers unless they're a section of RPN. RPN has its own sort of thing there, so no idea why these exist. They seem redundant and or computationally wasteful. So it's essentially just a regression, a refinement regression, and then non-Bayes regression into 2D points from 3D points. We go in our first level convolutional layers into RPN. We get some object proposals from there. Those object proposals get sent into the second layer, which does some more regression on it, running other convolutional layers through. You get a finer box, goes into the third layer. Same thing happens again at this layer. We get some other features of it, which I'm going to go over in data types. And you get nicer bounding boxes from there, non-maximum suppression, and then we do some part matching to get from 2D into 3D. So I'm going to be going back to this repeatedly. Overall, picture sort of ties everything together. So it's going to be a lot of flipping around. Data types, we have the car template. This uses CAD data as a reference for all of its learning. So we have models for a bunch of different types of cars. The cars have a bunch of points, X, Y, Z, and a general template size with weight length. Object proposals, basic bounding box. Center with height. Level 3 outputs. This is where it starts to get a little bit more interesting. The level 3 output has a 2D bounding box, and fully connected layers calculate all of the points in a 2D section that were from the CAD data. They augment their training data to get this. That's covered in a later section. But we get a bunch of points with X and Y in B, and then each of these have a visibility put into them as well. The potential states for visibility are visible, occluded by another object, self-occluded, and truncated. So whether you can see it, whether it's behind something else, whether it's behind itself, or whether it's just inside of the image. And then template similarity. Template similarity is what we use in order to figure out which of these cards is actually in the image. It's used later on in the template matching. So after template matching, yeah. Center of the bounding box, orientation, and size of the bounding box. So general region proposal network essentially ripped straight from the faster RCN paper. Inputs any size image, outputs a set of rectangles with objectiveness scores. I'm only going to cover briefly this part of it. It's one of the building blocks, so it's not really what they've added to the paper. Slides window with centers and anchors across the feature map. From there, we feed all of the potential regions into another convolutional layer. You get likelihood that it's an actual proposal and regressed bounding box. That's what gets sent on to the second layer essentially. Shares layers with different classifiers for ZF, and shares 5 first layers for PGD16, shares 13 first layers. And then, as you can see, it goes from the first shared conv layers to the feature map. RCNN takes that feature map, creates proposals. The proposal set gets sent out to the rest of the network. That was cut in half here, and from there you just get whether or not it's a piece. And they do all their figure out what it is over there. Total outputs from the faster RCNN region proposal is 6 times width times height times k. K is the number of different anchor boxes that we're looking at. So we get a hell of a lot of outputs from it. We don't very much. So this is one of the areas where this network is especially interesting. So they augment all of their training data. They do this by taking CAD models which have predetermined points. They look at the data set which they use PD for theirs. It's actually doing very well on PD right now, but they compare the bounding box in size, length, width, and height to all of their CAD data. They find the closest one that matches to it. They then orient the actual points in the CAD data and they project it onto the 2D plane so we can get the area here onto the 2D bounding box that's in PD. And then by looking at the CAD data, they get inclusion values for all the points. They do this automatically just in order to help their training because it would be just ridiculously difficult for someone to sit down and to individually find where all of these point values are on a data set. I don't know if you can pay me to do that, honestly, but they found a nice way to get it done quickly. For training, this is one of the fun areas of this paper is they tend to just reference other papers for a lot of what they're saying. Direct quote from it: "We use the faster RCNN framework based on RPN to learn the end-to-end mental model." My assumption is that they use the same training method, in this case, four-step alternating training and image-centric for grabbing their proposals. There are other things mentioned in the faster RCNN framework, approximate joint training and non-approximate joint training. In the paper, they actually said that they use four-step alternating for their submission and for their testing. I'm assuming that's what these guys said meant by.
Do you know why this? Why they say we use the same faster RCNN framework?
I'm assuming it's because they have the RPN in there and they're using the.
We used to use the same code
They
as
use the same-
faster RCNN, and did not change how the training file, the Python training file is.
I couldn't find the code for this. I searched.
Yeah, but they use the cafe model and they later played with the protocol file, but everything else is from faster RCNN. So
So
basically, the Python files that train this model, they don't even know how that functions. They just
they said.
yes, exactly.
So
I love this field.
I feel like I did more than they did for this on going through and figuring that out. But essentially, four-step alternating training method. They train the region proposal network. They train the detector network, and then they combine them with the shared convolutional layers. Those come from the detector. They combine it and they train the RPN specifically. They go through and train the rest of the detectors, fully connected layers. They do this repeatedly and eventually get something that's workable. They also have image-centric training, which is sort of different from what I've seen with a lot of other ones. They grab all their batches from one image. So individual proposals, they grab 256 anchors, one-to-one positive and negatives. If less than 128 positives exist, then we don't do it. Later on in losses, which I think is the next two, I'll explain what they mean by positive and negative. General loss functions, they have losses for each of the layers, layer 1, layer 2, layer 3. So each of these has their own independent loss function. Layer 1 just has RPN loss ripped from the other paper. Layer 2 has a detection loss and a part loss, which is interesting considering that we're not calculating for parts in layer 2. So why that's a loss at all, I don't know. It seems wasteful to train it to do something that it doesn't do, but I don't know.
So do we have the exact form of the parts loss?
Yep, I have it later on. And then layer 3, they have detection, parts, visibility, and template matching. All of these are the next one, loss function specific for only RPN. I tried to include as much as I possibly could, which wasn't fun to me, but it's on there now. So for the RPN loss, they have a loss associated with regularization. So the template regularization, you get all of these scale nodes from here. And they have one for whether or not it actually detected it properly. For regularization loss, they use robust smooth L1 loss, which follows this function over here. And for generally just for detection loss, they use this right here. These are the only two loss types that exist in this entire paper, so they have their own special little form of P for softmax, R for robust smooth L1. Yeah, so it's the RPN loss is 1 over the number of classified points times the loss function, which in that case the loss function is just all of these individual points here put through what is the ground truth and what is the predicted loss through the smooth L1 loss here. So each of those have their own loss associated with them. And then plus lambda hyperparameter divided by number of regularizations. And ground truth P1 times regularization loss, or sorry, regularization loss is over here. That one's just soft maps. Times the ground truth multiplied by regularization. This one over here, the anchor just makes it so that we're not putting a regularization loss on something that's not actually a true proposal. No sense trying to fix the box if it's not actually a box. But it is a box. You know what I mean?
Wrong pass.
Yeah.
Wrong pass.
So how do we know what EI is? What our predicted EI output is? So they say it's positive, or this is actually a true annotation of the highest intersection over union when it's the highest intersection over union overlap but with the ground truth. Or the intersection over union overlap is higher than 0.7 with any ground truth box. So you can have multiple true bounding boxes for one area, but you can also only have one depending on how many fit to build. And then loss function specific for DeepManta. One of the fun parts about this is if you look at the bottom here, X, XA, and X star are predicted anchored ground truth. When they go over here, they swap it. Stars are predicted, the other one is not. So I don't know why they did that. They just felt like it. But same basic losses and LCS and regularization are generally the same. They just don't have a loss associated with the anchor. So they're not calculating anchors. They don't need to figure out where that is. They only have a loss associated with the actual bounding box from here. So there's only X, Y, W, H. They don't have any anchors for this. Part loss is a little bit different. So this is the actual part loss in here. This is also in the layer 2. So why that's in there, again, I don't know. All they do is they just take the U and V for each of the parts minus the center of the bounding box divided by the width, and you get a bunch of points, and you figure out how different they are from the points that are supposed to be there.
So is the points like the centroid of the parts?
No, the points are, if I go back to this image,
Or just
here,
points from the CAD?
the points are from the CAD data, and
Yeah,
it's what
okay.
they projected
We're
on.
trying to learn
Yeah.
how to place these points, basically.
And again, why that's in layer 2, I don't know. They just decided that it was important enough that they wanted to keep it. It might be because they have shared layers, so they figure if they want to maximize the shared layers, they may as well make it so this one has a loss associated with parts. Yeah. They do that from, they don't actually do that with the network. If we go back to here, they do non-mean suppression, and then they do a matching algorithm that takes the points that they found in 2D and matches it to the 3D CAD data that they still keep CAD. So they need the CAD data not only for training, but during runtime as well. So depending on the number of vehicles, it can get a little bit, it should get a little bit taxing on storage, but I doubt that.
What about the run speed? Do there are any results about the run speed?
How fast?
How fast?
Yep, there's some, it's on Kitty as well. They have run speed for, I believe they submitted the one that they had for VPA 16, not Google Net, but it's relatively fast actually. They only had 15 types of cars in their CAD data set though, so relatively small. So that's, let's go back to here. Visibility loss, just whether you're right about if it's visible or not, and template similarity loss. Smooth L1 loss from just scaling of what the actual bounding box is. So template similarity loss gives you the length, width, and height. So just generally, which one it's closest to. You'll get a bunch of values out of this length and height. If it's closest to 111, that means it's closest in size to that actual number. So they more match the size of what they found back into the CAD. So
Why we drop on the bounding box on the What's the centers?
Or the bounding box centers, you mean over here? Why why they have the centers here and not over in the other one, or you mean the acres, or?
Why aren't they using log? That's the question.
Oh, I believe that's to regularize the size. They want it to scale down to.
It's a normalization, and it's for faster RCNN. It was proven that this formulation gives a more stable output, more stable learning. However, for MV3D, you literally use the redundant 8-box representation, 8-box because as well. So basically, this is just let's assume it as a normalization strategy. I think it's an overcomplication. Like you don't need it.
Yeah, it's a common trick in optimization to convexify the problem a bit, right?
So the reason why they did it is because they did it. That's what I'm assuming.
Probably.
And then parameters for all their hyperparameters, they set it to 1 except for lambda parts, which they set to 3. Later on, there are some tables that they just did some empirical tests. They found that worked well. So 2D to 3D matching, they take an algorithm that is within this specific paper. I didn't want to cover it because it would have been another 4 or 5 slides of just
Okay,
matching. So ON solution is rather fast, probably comparatively to the network, but for the template matching, they just grab the template similarity values, whichever one's closest to 1, 1, 1, they take as their part, and then they compare the CAD data to the 2D points, and they get the rotation and the rotation scale and all the other values. General performance. A lot of graphs in here. Hopefully they're visible. Table 1 is 2D vehicle detection and orientation on the Kitty validation sets. So they did very well with GoogleNet and with VGG16. They beat faster RCNN, sub-CNN, Mono3D, all of these other ones that I don't know about. And results for 2D vehicle detection on the Kitty test set, they did better with VGG16. So that's the one that they chose. And actually, no, I believe they submitted GoogleNet because the time over here is for VGG16, it takes 2 seconds. For GoogleNet, it takes 0.7. If I remember on the Kitty set.
Which is still a long time to actually perform sections.
It's relatively slow comparatively what you want for outputting FR, especially when there's other stuff you have to worry about as well. They have recall/3D localization curves of 1 and 2 meters. They basically beat Mono 3D on this, and they do lose in distance localization to 3DOP, but that's a stereo technique, so essentially, of course, they did.
Are you sure that they are comparing just to the stereo version, or there's multiple versions that they did 3D?
Yeah.
Right?
So over here is the 2D area for 2D detecting set on Kitty, and then 3D and in 3DOP they have said that it's type stereo.
Okay.
So they just copied what's in Kitty.
No, so this isn't comparing with their LiDAR version.
No.
Yeah.
So it is just a stereo one.
Yeah. It's also.
They do win at 1 meter though. So they lose at 2 meters to this one, but they do win at 1. Unfortunately, there's no value for how this one does at 1, so we can't really be sure, but it's highlighted black. Performance in Kitty, it's currently 11th place in object detection and evaluation for cars, 2D, and first place in object detection and orientation evaluation for cars. Overall, it's one of the faster ones at the top. There's 1 or 2 that are beating them. I believe that there's one that's 0.15 seconds in the 3D orientation section. But aside from that, I think they're 3rd or 4th fastest up at the top. So general contributions, they use CAD data to modify the training set and find 3D orientation. They do find point estimations. So it's not just where's the bounding box, should we avoid that? They can generally see what the shade and avoid specific components of the car. And it's also quick for how high up it is and accurate results on the data set. Conclusion, interesting approach. They could most likely add support for other types of objects, pedestrian cyclists, if they modify the meshes and add CAD data, because realistically, it's just matching points. So you should be able to have those modified. I don't know if it'll change the network being deeper, but they may be able to add in CAD as long as the number of points is consistent for general pedestrian cyclists. And the point cloud / CAD data is an interesting approach, but it does rely on cars being somewhat consistently shaped, because if there is, say, an outlier car in the Kitty data set that has a similar size bounding box to what their CAD data says, they're going to match the points immediately on it, and that's not a very good representation. So because they're augmenting the data set with what they have, you can't be 100% sure what the point is. So that could lead to some issues with testing and training, and possibly overinflating what they've actually found in their results. So odd vehicles may lead to odd results, but that's the same with any learning in general. If you haven't seen it, you're not going to do well on it. General references and questions.
So this strikes me as reviving classical computer vision and fusing it into deep learning, right? Like next is deformable parts models, no?
Yeah, I think that essentially
I mean, it's 3D, which is a big deal, right? But it's pretty cool.
yeah, one thing that is interesting about it is it is only just cars. So there's a bunch of work that could be done with just changing the outputs that the box, the classification in there is just car and non-car. Add a little bit more in there, but it's just making your regions as nice as possible. It's the only real thing that I found. And
Also, it's only tested on kidney, so
yeah,
we will never know if it's actually without it or not. Because doesn't mean anything if you test on a single data set, right?
but they did do the validation. They included both of the parts.
The validation is part of the same sequence as our for kidney. They try not to mix up test and train data, but the areas they collect both are basically the same, so it's not a big difference. It's not like training on a data set in North America and then testing on it, right? Yeah, definitely. Good job.
Okay, I think we're done for the day.
We're done for the day. I wanted you send me everything. Okay. Next.